Triple integrals in cylindrical coordinates. So as we saw with double integrals, sometimes it was advantageous to use polar coordinates to integrate. And this was the case when the region of integration was circular, and also when the integrand contained terms like x squared plus y squared. Okay, well, we have a similar concept with triple integrals, but we use cylindrical coordinates. And what are cylindrical coordinates? Well, basically, they are polar coordinates with a z-axis. That's pretty much the quick way to tell you what cylindrical coordinates are. You could see here we have a point in xyz in black there, and we could describe it in terms of r, and theta, and z. But be careful what this r means, okay? This r is not the distance from the origin to the point. Absolutely not. It is instead the distance from the z-axis, okay? So the distance from the z-axis, which you're seeing there highlighted, is going to be the r value. Later on, we'll discuss coordinates called spherical coordinates, which actually do have one of the variables being the distance from the origin in 3D space, but that is not what r is now. Moreover, if you start with the x, y, and z, okay, and you want to get r, theta, and z, well, here are some formulas to convert from rectangular to cylindrical coordinates. Of course, you have to be careful with arctan. You have to peel your eyes to see which theta you're actually solving for. And likewise, if we want to convert to x, y, and z, but from cylindrical coordinates, we may use these formulas there. So these are triple integrals, and we know with triple integrals, we break up our region of integration into small 3D objects, okay? When we dealt with rectangular coordinates, we broke them up into these rectangular prisms, and we got that the volume, at least formally, okay, it could be expressed as dx dy times dz. Okay, you get a if each of these differentials were physical quantities and they had units like meters, you would get a meter cubed there. Well, now we'll have to break up our domain of integration or region of integration into these wedges, okay, these cylindrical wedges we call them. And let's compute the volume element for that. And what is the volume of this small wedge when as the limit, in the limit that this becomes an infinitesimal volume? Well, the outer arc there has a length of r d theta, okay? And this, again, if we were thinking about these in terms of physical quantities, theta doesn't have a unit, r does. So this has units of meters. R d theta would have units of meters in that case. And so that's the length of this outer part there. We also have dr, the width along the r variable, and we have dz, the height along z. So multiplying these three things out, we get our volume element in cylindrical coordinates that we could use in our integral, in our triple integral. So here we have the theorem for changing variables of triple integrals into cylindrical coordinates. And if we could describe our region of integration D in 3D space in this manner, so that Z is bounded by surfaces that are functions of x, y, and that R may be bounded by functions of theta, and theta is between alpha and beta, then we could express our triple integral this way. Some things to pay attention to is that these bounds were gotten by the description that we gave of D above, and that we we plug for x, for our function. If it's anywhere we see an x in our function, we would plug in our cosine theta instead. Anywhere we see a y in our function, we plug in our sine theta. And anywhere we see a z in our function, we plug in z. Okay? That's what that means there. And this last part is just the volume element. Okay? And we have that dv is r dz dr d theta. And so this is our volume element. Make sure not to forget that r. Okay? Sometimes it's easy to forget that because when you convert this function, you'll get now a function in terms of r, and it's easy to forget that this extra r, which is coming from the volume element. Okay? But it's very important, so do not forget it. So let's take a look at an example of using cylindrical coordinates to do a triple integral. So we want to find the mass of a solid D bounded by the paraboloid shown here, z is a function of x, y, and the plane z equals 0. And we are given that the density is equal to 5 minus z, so that as z increases, the density decreases. Okay? One way to think about it is that it's heavier near the base at z equals 0 than it is near the top. So what we need then is the triple integral. That will give us the total mass. Okay, density times volume gives you mass, and then this triple integral is summing over the entire solid D. And for visual reference, this is the solid D that we will be integrating over. This is not the function that we're integrating. Okay, the function is 5 minus z, which if we were to represent in this plot, we would represent with color, for example. So if we let red be where it's less dense and blue be where it's has a higher density, then we would get bluer colors near the top of our solid, and at the bottom it would be more red. That's how we would represent the function of 3 variables, which gives us the density. But what you see here is in fact the region of integration. So how do we convert to cylindrical coordinates? Well, before even discussing that, why should we convert to cylindrical coordinates? Well, something to notice here, that the domain given by the by this paraboloid as a bound for it looks like it has this minus x squared minus y squared, which could be factored to minus x squared plus y squared. Well, that would be equal to r squared in cylindrical coordinates. So the first thing to note is that the domain itself works for cylindrical coordinates. It's simplified if we use cylindrical coordinates. Secondly, we have to look at the integrand. Now the integrand is quite simple, but clearly it could be integrated easily using cylindrical coordinates. So even converting to cylindrical coordinates would be rather trivial here, since we don't really have x and y being used in the expression, but the function itself would not become difficult to integrate if we use cylindrical coordinates. So due to the domain and the function being amiable to cylindrical coordinates, we will integrate using cylindrical coordinates. So the first ingredient will be describing the region in cylindrical coordinates. So notice here that this solid is bounded by the paraboloid and the plane z equals 0, so the xy plane. Well, let's see where these two intersect in order to get bounds. we see that they intersect at the circle of radius 2. Okay, so where this paraboloid meets the xy plane is at the circle of radius 2. That's going to be important for our double integral after we carry out the first integral. So our domain of integration can be expressed in this manner in terms of cylindrical coordinates. R will be between 0 and 2. Theta 0 to 2 pi, because the paraboloid intersects at a circle, and so our region of integration for the double integral will be the disk of radius 2. And z will be between 0, the z equals 0 plane, and 4 minus r squared. Where did we get this 4 minus r squared? Well, that's what happens that's what we get when we convert 4 minus x squared minus y squared into cylindrical coordinates. So this then is our first ingredient. It is the description of the region in terms of cylindrical coordinates. The second ingredient for converting to cylindrical coordinates and carrying out the triple integral is to convert the integrand or function to cylindrical coordinates. Okay, and when I say integrand here, I mean the integrand when it's when rectangular coordinates are used. Okay, and we'll see why I make this emphasis in a second. So how do we convert then the function? So here's our function, 5 minus z. Well, wherever we see a x, we substitute r cosine theta. Wherever we see a y, we substitute r sine theta. Wherever we see a z, well, we just let it be z. All we see is z in this expression. All we see is z. There are no x's and y's. So, in fact, in cylindrical coordinates, it's 5 minus z, which is the same as in rectangular coordinates, but that's just a coincidence because x and y do not show up. And finally, the third ingredient is using the volume element that we found for the wedge above. Okay, so we use the volume element given here and the other ingredients into our formula. Okay, the formula above over here, F being converted, the volume element, and the bounds. So we get the bounds from where? They're in blue, because we get them from ingredient 1. Okay, so notice here that z is being integrated from 0 to 4 minus r squared. R is being integrated from 0 to 2, and theta is being integrated from 0 to 2 pi. Second ingredient is the function converted to cylindrical coordinates. That's what shows up in here. And we have it in green there, 5 minus z. And the last part is the volume element, and that's what we have over here. And now I talked about the integrand before because you could view this whole thing as the integrand with the additional r that comes from the volume element. So that's why I made that distinction when I said integrand. I meant integrand that you would have in terms of rectangular coordinates. Now our integrand includes this r that's coming from the volume element. So our integrand in cylindrical coordinates is not merely the conversion of the function, but also includes terms that come from the volume element. Okay, so let's integrate then with respect to z. We would get this expression here. Plug in your bounds. Plug them where? Plug them into z, okay, the variable that you just integrated. And we'll be left with this expression. Carry out the integral now in terms of the variable r, and simplify, and you get 88 pi over 3. That is how you take a problem that was in rectangular coordinates and do the triple integral in cylindrical coordinates.